Hi, Assalamualaikum and a very good day. So today I'm going to do a little bit revision on the formula of supercapacitor versus supercapacitor because most of the comment I got from the YouTube they asked to clarify the formula for supercapacitor. And in this video, I would like to clarify some of the formula for supercapacitor and supercapacitor. So as you can see from the table here, okay, so the left hand side is the formula for supercapacitor, while for the right hand side is the formula for supercapacitor. The only difference based on specific capacitance is one of them we are using the formula of farad per gram, and the other one the formula is coulomb per gram or milliampere hour per gram. So let's start one by one. So we go to supercapacitor first. So this is basic formula. The number one is basic formula to calculate specific capacitance. Normally we are using our analysis, which is cyclic voltammetry. From the cyclic voltammetry, we can get our CV curve or cyclic voltammogram curve or curvature or arc. We can call whatever you want. So from here, you can calculate area under the graph. So basically, what we got here, this is the integration of the graph. So you will get here is the area. So the area you will divide with S, which is the scan rate, and divide also with the mass of your sample, because you're going to calculate the gravimetric capacitance, which is farad per gram. So that's why we are using mass, and also here V is your potential window. So this is important to get the specific capacitance from the cyclic voltammetry analysis. Area must divide with the scan rate times with the mass and also with a potential window. It is applicable for 3 electrode system and also 2 electrode system. So if you using CV as your analysis, you can use this formula both for 3 electrode system and 2 electrode system. And someone might say, I found in the journal online, basically they put number 2 here. So why? What happened? So actually, the presence of number 2 or without number 2 depends on your mass, how you get your mass. For example, for 3 electrode system, you just depend either you study positive or not negative electrode. So just get the mass of the positive or negative electrode. So you no need the number 2 here. If you study 2 electrode system, means that you rely on the 2 mass, the mass at the positive and also the mass at negative electron. So that's why this mass you must add on positive plus the mass of negative electron, then the mass divided by 2 to get the average mass. That's why you can find some formula have number 2 at above, because they are using mathematical arrangement m divided by 2. So number 2 they put at the nominator instead of denominator. So it's just based on how you get the mass. If you want to do the mass outside the calculation, you just take the average mass, so no need the number 2 here. And so this is the clarification. So you can use this formula for 3 electrode and 2 electrode. It doesn't matter. Just make sure the mass is correct. For 3 electrode system, you can choose the mass of your electrode. However, for 2 electrode system, the mass should be average mass if you want to use this formula. So I hope you understand that. Okay, that's for CV. So a lot of researcher actually occupied also specific capacitance value based on galvanostatic charge discharge GCD. Because based on GCD, so this is a typical graph of GCD. It's like a triangle. So triangle. So for GCD, it mimics the real application of the battery or supercapacitor, because you can see the process of charging and discharging. That's the whole point of the GCD. So from GCD, the important things you can get is the discharging time. Okay, then you can also extract the amount of current, because before you start your experiment, you determine the amount of current based on your mass. When your mass, you divide your mass ampere per gram. You divide the amount of current by the mass, then you get current density. So you can get the value of current if you fix the current density value and also the mass of your material, then you can get the amount of current. So it's important. So the formula for GCD, so focus at number 2 here. For GCD, what you should focus is, so you should have the value of current. So because before you start your GCD measurement, you need to input the value of current. So take note and use that value of current. And delta T is your discharging time. Based on your GCD curve, your discharging time. Discharging time follow from your maximum potential window to your minimum potential window. That is your discharging time. So divide by the mass, of course the mass, and also delta V, which is your potential window. Okay, against the same in this case. Sometimes you might see a formula has number 2 at the nominator. So why? Because of the mass. If you use 2 electrode system, you should have average. Okay, someone might not calculate the average outside the calculation, so that's why they put number 2 here. So depends on your solution, whether you are using 3 electrode or 2 electrode system. For 3 electrode system, no need to have number 2 here. For 2 electrode system, you can have number 2 if your mass is the addition between positive and negative electron. If your mass already average between positive and negative, no need to have number 2 here. So it depends on your understanding and your clarification, because when you give the formula, you need to clarify in your journal what is the value of M stand for. So remember of that. Okay, I think enough for supercapacitor, for specific capacitance, because I just got a question on how actually to clarify based on the formula on supercapacitor, specific capacitance. For specific energy and specific power, I will go for the next video. Okay, let's go for quick for supercapacitor. So let me label here number 3, and this one is number 4. If you see the left-hand side, which is supercapacitor, and supercapacitor is right-hand side, the only difference to calculate the specific capacity here is the absence. I can see that this is the absence of V, which is the absence of potential window. Because specific capacity is the same. It's the amount of charge that can be stored inside or within your material, but not limited to the potential window. You're not limited to 0.5, 1.0 volt. So it is the capability of your material to store charge without the limits of the potential window. That's why most of the journal right now, they calculate the ability to store charge in terms of specific capacity. But I'm not be a denial here. There are a lot also calculate on farad per gram. They have a different opinion in terms either should calculate farad per gram or coulomb per gram or milliampere hour per gram. So both does not falls to correct or wrong. They have their own judgment. So mostly, as you can see, if your material have battery type, if your material have obvious redox, they go for supercapacitor and they calculate based on the specific capacity. Same, this is for cyclic voltammetry, and same for number 4. We are using GCD also to calculate the specific capacity, whereby here also absence of V, as you can see here. They only have currents time with discharging time divided by the mass. Okay, so it's quite simple and quite straightforward. So I hope after this, no one asking we should have a number 2 or not to put in our formula or not. So it's depend on your math actually. Okay, that's all I think. I hope everyone understand and can calculate the formula correctly. That's all. Bye. Good night.